Applications of Kohlrausch law. There are two applications of Kohlrausch law. If the conductivity of ions is known, then conductivity of weak electrolyte at infinite dilution can be determined, or the limiting molar conductivity of a weak electrolyte can be obtained by making use of limiting molar conductivity of the individual ions. And the formula is limiting molar conductivity of an electrolyte is equal to, of a weak electrolyte is equal to number of cations multiplied by limiting molar conductivity of cation plus number of anions multiplied by limiting molar conductivity of anion. This is one application of Kohlrausch law. The second application is dissociation constant of weak electrolyte can be determined from the limiting molar conductivity and the molar conductivity value. This is the dissociation constant of weak electrolyte, and this is equal to concentration of the weak electrolyte multiplied by square of its molar conductivity divided by limiting molar conductivity multiplied by, in brackets, limiting molar conductivity minus molar conductivity. Using this formula, dissociation constant of weak electrolytes can be obtained. So these are the two applications of Kohlrausch law. Now example, calculate limiting molar conductivity for calcium chloride and magnesium sulfate from the data given in table 3.4. In table 3.4, the conductivity of various cations and anions is given at infinite dilution. So what will be the limiting molar conductivity of calcium chloride? Calcium chloride dissociates to give 1 mole of calcium ions and 2 moles of chloride ions, or 1 calcium ion and 2 chloride ion. Therefore, its limiting molar conductivity will be equal to 1 into lambda naught calcium ions plus 2 into lambda naught chloride ions. Putting the value of conductivity of calcium ions and chloride ions, the limiting molar conductivity of calcium chloride is 271.6 per ohm centimeter square per mole. Similarly, magnesium sulfate. Magnesium sulfate dissociates to give magnesium ions and sulfate ion. 1 mole of magnesium and 1 mole of sulfate ion, or 1 magnesium ion and 1 sulfate ion. तो इसकी limiting molar conductivity हो जाएगी, this will be equal to lambda naught magnesium plus lambda naught sulfate ion. Putting the value of limiting molar conductivity of magnesium ion and sulfate ion, limiting molar conductivity of magnesium sulfate is 266 per ohm centimeter square per mole. Next example, limiting molar conductivity of sodium chloride, hydrochloric acid and sodium acetate are given. These are the values. Calculate lambda naught for acetic acid. AC stands for acetate ion. AC minus stands for acetate ion. Lambda naught value of HCl, lambda naught value of sodium acetate and lambda naught value of NaCl is given. And we need to find the lambda naught value of acetic acid. Here AC stands for, AC minus stands for acetate ion. Now, to find the lambda naught value of acetic acid is made up of the ions H plus and acetate ion. From the values of lambda naught HCl and lambda naught sodium acetate, we can obtain the lambda naught value of H plus and acetate ion. So just add the lambda naught value for HCl and lambda naught value for sodium acetate. On adding this value, we add the lambda naught value of H plus and acetate ion, but lambda naught value of Na plus and Cl minus ion are also getting added while adding these values. So you need to subtract the lambda naught value of NaCl from this sum. Lambda naught value of Na plus and Cl minus ion is not needed. So just subtract the lambda naught value of NaCl from this sum and you get the lambda naught value for acetic acid. The trick is just add the lambda naught value of those electrolytes which are giving the required cation and anion of the electrolyte whose lambda naught value has to be determined. And from the sum, subtract the lambda naught value of the electrolyte which contains the cation and anion which are not needed. So putting the values and solving, the lambda naught value for acetic acid is 390.5 per ohm centimeter square per mole.